In this capstone, you'll bring everything together: blockchain identity, wallet signatures, backend verification, and access control. By the end, you'll have a practical passwordless login flow that is secure, usable, and ready to prototype. So far, we've covered the building blocks: trusted blockchain data, public key identity, wallet-based signing, app integration, and security controls. Now we'll combine them into one complete passwordless dApp login flow. Before we touch code, it helps to understand the full authentication story. For the user, the flow should feel simple: arrive, connect a wallet, approve a message, and enter. Behind the scenes, each step has a security purpose: create a fresh nonce, verify the signature, establish a session, and protect roots and roles. If that story is unclear, the result can be confusing prompts, reusable messages, or weak access control. Passwordless login replaces a shared secret with proof of wallet control. The user connects a wallet, and the app reads the public address. Before signing, the backend creates a one-time nonce, so an old signature cannot be reused. The wallet signs a message that includes that nonce locally and securely. Then the backend recovers the signer from the signature, compares it to the claimed address, and creates a normal, authenticated session only if they match. The flow begins with a simple capability check. Does the browser expose a compatible wallet provider? If it does, the app should ask the user to connect, not connect silently. The wallet prompt returns an address and permission to communicate with that provider. Keep that address as temporary front-end state. A connected wallet identifies an account, but it does not yet prove the current visitor controls it for authentication. Once the front-end has the wallet address, it asks the backend for a nonce, for example with get auth nonce address equals. The backend creates a random value tied to that address and returns it with an expiration time. This value must come from the server, not the browser. When the user signs the login message, the nonce proves the signature is fresh. After verification, mark the nonce as used, so a captured signature cannot be replayed. The sign-in message should be understandable, not just cryptographic noise. Include the application domain so the user recognizes who is asking. Include the wallet address so the approval is tied to the right account. Add the nonce and issued at time so the signature cannot be reused later. Finally, state the purpose in plain language, such as sign in to example dApp. Vague or alarming messages train users to click blindly. Next, the front-end sends the exact sign-in message to the wallet. The wallet displays it to the user, including the nonce, so they can confirm what they are approving. When the user signs, the private key never leaves the wallet. Instead, the wallet creates a cryptographic signature tied to that message and account. The front-end receives only the signature, then sends it to the back-end for verification. After signing, the front-end sends 3 items to the authentication endpoint: the claimed address, the original message, and the signature. This is a trust boundary. The backend must not accept the address just because the browser provided it. It checks the nonce, verifies the signature, and confirms which address actually signed the message. Only after that confirmation should the application treat the user as authenticated. On the backend, the trust check is strict. First, confirm that the nonce is real, unused, and still valid. Then verify the signed message and recover the wallet address that produced the signature. That recovered address must exactly match the claimed address. If the nonce is expired, reused, malformed, or the addresses differ, reject the request. Only after these checks pass should the server create a session or issue an auth token. Once the signature is verified, treat it as a one-time proof and convert it into an application session. The backend should create the session only after verification succeeds, then store it securely, either server-side or in a signed token. If you use cookies, apply protections like HTTP only, secure, and same site. Link the session to both the wallet address and your user record, so future requests can be authenticated without repeated signing. Proving wallet control does not mean automatic access to everything. The wallet address is an identity signal, not a complete authorization decision. Before returning protected data, running an admin action, or opening a member area, apply authorization rules. Those rules might come from roles, explicit permissions, token ownership, or off-chain records. Check access at the resource boundary every time, not only during login. The front-end's role is orchestration, not trust. In TypeScript, keep the login as a clear async sequence. Connect to the wallet, read the selected address, request a fresh nonce from the backend, build the exact sign-in message, ask the user to sign, then submit the address, message, and signature. After that, treat the backend response as the source of truth. Success establishes authenticated state. Failure should lead to a safe retry path. Before you ship, review the flow as both a security system and a user experience. Confirm that each nonce is single-use, expires quickly, and is verified on the backend before any session is created. Be transparent about wallet data and store only what you need. Make prompts, errors, loading states, and cancellations clear. Offer alternatives for users without wallets. And remember, if the backend did not verify it, the user is not authenticated. You've now connected the full passwordless login lifecycle: wallet connection, nonce, signature, backend verification, secure session, and protected access. The goal is balance: cryptographic trust enforced on the server with a clear experience for users. From here, build a demo, deploy carefully, study CWA, and explore production identity systems.